Hello, my name's Scott Summerfield. I'm the worldwide head of Bioanalysis at GlaxoSmithKline. I'm a senior director. I have a group at Upper Merion and Ware, and this is the site in Ware in the UK that I'm based. I lead an organisation that supports the bioanalysis of patient samples. So we support early GLP studies, non-GLP studies and clinical studies. That's small and large molecule, and I'm accountable for the work that's done internally and also externally. You know, I think even now it's talking to people about the science that they do. You know, there's lots of pushing of paper around, but you know, it's really good to just talk about the things that make methods work, or you know, solve analytical challenges that we're facing. Well, something that amazes me is that, you know, every few years we see new modalities come forward, whether they're small or large molecules, and it just astounds me how innovative sort of chemistry and biology is, and you know, that brings new bioanalytical challenges that maybe we hadn't even thought of before with regard to separations or new extraction techniques. So I'm just amazed that we keep seeing new modalities come forward to challenge us. Some of the technologies that are emerging in the field of bioanalysis are really around process improvement. And if you imagine the bioanalytical process as a pie chart, so you have the sample logistics element, you have the sample preparation in the lab, the analysis, and then the data manipulation. And really a lot of the technology is looking at where the bottlenecks are. So in the lab area, preparation of calibration curves and QCs with new liquid handling approaches such as the D300, which is kind of based on inkjet technology. And in the mass spec area, high resolution mass spectrometry, because the method development and time to run the methods is faster. And also I think faster chromatography, sort of sub-minute run times, are perfectly possible. I think the issue is actually us, not the technology now. If you look at liquid handling, like the D300, I mean, that can spray a calibration curve in seconds relative to a human, from nanoliters to microliters. And so that's a relatively quick process, even against one of our fastest analysts. The challenge is there's no regulatory precedent. These aren't pipettes. It works like an inkjet printer. So it's not particularly easy to calibrate in the sense of a pipette. So I think we're going to have to look at new ways to convince regulators that those data are fit for purpose in terms of accuracy and precision. The mass spectrometry front, we face a similar challenge. High resolution mass spectrometry has been talked about for bioanalysis for well over a decade, but no one has taken that information to a regulator. So we face that issue of the first time. In high-res mass spectrometry, you generate more information than just you tend to generate an entire spectrum. So there's issues with where the rest of that data, what that data is used for, if that's validated to be used. Can you even use that in, say, an ISR investigation? So I think most of the issues now come down to the implementation in a regulated setting, as opposed to the technology itself being fit for purpose. So I think the big conundrum that we face is that as new automation technologies come along, we start to generate islands of automation. So you have a small amount of manual intervention, then an automation step, then some manual step, maybe moving plates around, then some automation. And I think the challenge is how we merge those into a true end-to-end process. And that's not because I don't think that bioanalysts in the lab aren't important, but I think, you know, the industry is facing quite large challenges in terms of throughput and cost pressure. And I think that the biggest value in bioanalysis often is in method development and validation, and really putting our energy into where the methods can be made super sound, spend our time there, and maybe let the heavy lifting part of the sample analysis be done by sort of end-to-end robotics. So just following on some of the challenges around the regulations. it's very easy to calibrate a pipette. You know, you can take a certain volume of water and weigh it gravimetrically, so you can show a pipette's calibrated. When you spray 20 nanoliters into a liquid, you know, that's very difficult to do because gravimetrically the differences are too small to measure. So I think for techniques like that, we have to look at different ways to calibrate, or convince the regulators that maybe if we have two separate devices that are pipetting or spraying liquid, that we get that ability to show accuracy and precision by inference of having two independent D300s or whatever the analytical technique is, you know, that we're doing the liquid dispensing, and use that as the reference point. Or that we trust in, say, the inkjet technology, that if it didn't work, then, you know, we wouldn't get nice pictures from Hewlett-Packard at 600 dpi that we can print at home. So I think we have to trust in the technology more for that one. In the high-res area, I think a lot of the issues we cause by ourselves. And that's because we pontificate on what happens if this occurs, what do we do with that piece of data. But, you know, GLP and the regulations aren't that prescriptive. I think if you look at GLP at its essence, it's really explaining what you did and why you did it, and having a sound scientific rationale. So if you took a high-resolution chromatogram and quantify that, and then needed to use something else in that chromatogram, I think the documentation is the way to convince the regulators. And maybe at some of the larger conferences like RIB, beginning that debate with them now, and showing them some of the technologies that are emerging and getting the discussion done today, so that when those molecules hit filing in 5 years' time, they're prepared for what we're about to send them in the filing.